Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on vectors. Now in this particular presentation we're going to move on from the dot product of two vectors and we're going to introduce a new way of multiplying two vectors together. So in the previous presentations we talked about the dot product where you multiply the corresponding components, add them all up and you get a number. Here we're going to talk about a way of multiplying two vectors that gives you a vector as your answer. I'll do an example and we'll talk about the geometric meaning and motivation for such a multiplication. So let me share my screen with you. Okay, the cross product of two vectors. All right, so we already know how to multiply a scalar or a number with a vector. Okay, we know from previous videos the dot product of two vectors. Well, in this presentation I'm going to show you the idea of a cross product, which is another sort of very loose way of defining multiplication between two vectors. Okay, so suppose I've got two vectors in three-dimensional space with their components. This big mess here is how we define the so-called cross product of A with B, or A cross B. Okay, now remember the ijk's here are just the standard unit vectors in three-dimensional space. Okay. Now, people who look at this definition here freak out because there's lots and lots to remember here. Okay, but when I show you how to compute this, say from an exercise, you don't have to remember this. Okay, because you can just use a computational process that involves an idea called determinants. Now, you may not have heard of a determinant. I'm not assuming you know anything about a determinant, but I'll show you those as we go through. Okay, so the first question is, these look quite bizarre and complex and abstract. Why would we want to multiply, define this sort of cross multiplication to be this? Well, geometrically, what this cross product does is produce a new vector that's perpendicular to both the A vector and the B vector. So let me just draw a little diagram here. Okay, this is a very loose diagram. Suppose I've got a vector A here and a vector B there. Now, there's two ways you can get a normal vector to both of those, or perpendicular vector to both of those. You can either point up like that or down like this. In this situation, the cross product will produce a vector that points in that direction. Okay, and it will be sort of jointly perpendicular to both A and B, or the plane that both A and B belong to. Now, if these are switched around and say that's your vector A and that's your vector B, then the cross product vector will actually point in the opposite direction. Okay. Why is that? Well, you can link the geometry here, whether it's pointing this way or this way, with the sort of ordering, if you like, of the A and the B. Okay, so, and it's called a right-hand rule. So the easiest way I can do it is just with my sort of hairy fingers. Imagine my index finger, or my pointer finger, is the vector A. And my middle finger is the vector B. Now, if I stick my thumb up, wherever my thumb points, that will be, it's pointing straight up towards the camera, right, away from the page or away from the screen. That is the direction that the cross product of A with B points in. So let's say I flip them around like in this model here. That's my A, that's my B, and my thumb will be sticking into the screen or into the page. Okay, so it's called the right-hand rule. Very, very nice rule to tell you which way the cross product vector is pointing. Okay. All right, so I've got a couple of things to explain. I've got to talk about determinants, and then I really do want to convince you that this vector, this cross product, is perpendicular or normal or orthogonal to both of these vectors. I'll do that a bit later though. Okay, so I'm going to just tell you that this kind of notation, okay, so here we've got sort of 4 entries and these vertical lines. This is called a determinant of a 2x2 system or 2x2 matrix. And to evaluate this, it's just, you just multiply diagonally. So it's this times this minus this times this. Okay, and the reason why I'm showing you this is because we're going to use determinants to derive this for specific examples. So you don't have to remember this crazy mess here. Okay, so let me show you an example. I'll come back to talking about this a bit later, about the perpendicularity or the orthogonality. But let's actually do a concrete example and see how we go. If A is this vector and B is this vector, compute their cross product. Okay, so watch carefully, because what I'm going to do now actually works for every example, and it's just an algorithm that helps you compute the cross product without having to memorize this mess. Okay? All right. So firstly, I'm going to write out what's known as a 3x3 determinant. Now, yes, okay, this is a 2x2, but we really need a 3x3. But to evaluate that isn't much problem. So what I'm going to do is I'm going to take the sort of basis vectors I, j, and k and write them in a row. Okay, I'm just going to write them as I, j, k. Then I'm going to take the components of the vector A and write that as a row beneath it. And then I'm going to take the components of B and write that as a row beneath that. Now what we have here is a scaled up version of this 2x2 determinant. So how do I evaluate this? Is the determinant of a 3-row and 3-column matrix, if you like. Okay, it's not hard. It's just a little game that I like to play called cover up. Okay, you start with this top left-hand entry, I, and you cover up the column and the row that I is in. And what have I got left? I've got a 2x2 thing which I will take the determinant of and multiply by the I. Okay, so I'm going to write I down, and I'm going to multiply that I. I'm going to cover up the top row and the first column, and I'm going to multiply I by the determinant of what's left. Okay, this is just purely algorithmic. Okay, then I'm going to move on to the J. We're going to do something a little bit different with the J. I'm going to put a negative sign out the front. Okay, now having a negative sign there means I can just use the standard determinant that I defined over here in the calculations. All right, so let's do the same thing. Cover up the column that J's in and cover up the row that J's in. And if you have a look at what's left, I've got 5, 1, 1, negative 2. Multiply negative J by the determinant of that. Okay, 5, 1, 1, negative 2. And now let's move on to the K. So I'm sort of moving along this top row here. The K, cover up the row and the column that K lies in, and I've got this sort of 2x2 determinant left. So I'm going to multiply that by K. All right, so if I cover that up, I'll have 5, 0, 1, negative 3. All right, so that's a little game I like called cover up. It can't get much simpler. It'll work every time. Don't forget the negative sign here. Okay, we need a negative sign there because otherwise we wouldn't be able to use a standard 2x2 determinant for that one. Okay, so let's move on. Let's evaluate these determinants by multiplying diagonally. Okay, so that times that minus that times that. I'm going very slowly because this is the first time I'm showing this, and once you know it, you can transfer it to many problems. Okay, 5 times negative 2 minus 1 times 1. Okay, 5 times negative 3 minus 0 times 1. So all we need to do now is simplify what's in those brackets, and then I'll have a vector as my answer. Okay, so I've got 0 plus 3, so I'm going to get 3i. Here I'm going to get negative 10 minus 1, and I've got a negative sign out there, so that'll reduce to plus 11j. Negative 15 minus 0, so I get negative 15k. Okay, if you wanted to write that as, say, a column vector, it would be something like 3, 11, negative 15. Okay, that's it. That's all you have to do. Okay, play cover up, move from letter to letter, and go positive, negative. If it was a bigger system, you would go positive, negative, positive. Next one would be negative. Okay. All right. Let's compare our answer with this horrible mess up here. Okay. So let's call this I don't know, star or something. Okay. So compare with star from the previous page. All right, what we want to do, so that's A1, that's A2, that's A3, that's B1, that's B2, that's B3. So if you go through and you cross multiply out, so A2, B3, well, that's A2 0, so that first term will be 0. A3 will be 1, B2's negative 3. So that times that will give me negative 3, and then minus sign will give me positive 3, which is what I've got there, positive 3i. Okay, and if I continue through, you'll get both of these terms. Okay, so it aligns with this crazy formula here. Okay, so I'm going to show you now why the cross product of two vectors produces a new vector that is perpendicular, normal, or orthogonal to each of the original vectors A and B. Okay. All right. Now, I'm not going to derive this. I'll save that for another presentation. Okay. So because it actually takes quite a bit of time, but I can still show you that this form produces a vector that's perpendicular to both A and B. All right, so let me show you how that works. So the claim is, if I define, say, the vector to be the cross product of A and B, that this cross product satisfies the following. Okay, we know from our videos on the dot product that two vectors are orthogonal or normal or perpendicular if their dot product is 0. Okay, so I'll prove this case, and I'll leave this case for you to prove. All right. All right, so C dotted with A is just A cross B, just by definition, dotted with A. All right, so let's go back to this crazy formula here, and I can say write these out as columns, and then I'll take the dot product. The dot product. So A cross B will have this as its first entry or first component. Okay, down here I'll have something like, well, let's put the minus sign in. And down here I can just put that in. And say A has just the A1, A2, A3 as its components, and now I know that with the dot product, it's that component times that, plus that component times that, plus that component times that. So with a little bit of algebra, we can hopefully work this out and simplify it. So let's just do that. Okay, plus minus, oops, sorry, that should be A2. Yep. Plus A3, A1, B2, minus A3, A2, B1. So now all we want to do is look for the cancellation. Hopefully I haven't made a mistake here. So A1, A2, B3, that's going to cancel with that one. Okay. A3, B1, A2, that's going to cancel with that one. And fingers crossed, this one cancels with this one. Yes, it does. Okay, so that is 0. Hence, this is true, and so C, which we've defined to be A cross B, is perpendicular, normal, or orthogonal to vector A. All right. Similarly, if you go and do the calculations, you can show that this holds that. That A cross B is perpendicular to the vector B. All right, but it still doesn't tell you, I mean, it works, right? It still doesn't tell you where this comes from. Okay, so let me just shed a little bit of light on it. I'll do another video about this, but it takes a little bit of time to show you. Suppose you want to find a vector C that satisfies both of these things. So you'd write out, C as C1, C2, C3, and go through and try to solve these two equations for C1, C2, C3. If you do that, that'll lead you to a vector with this as C1, with this as C2, and with the negative of this as C2, and with this as C3. So that's how it arises. But I'll show you that in another video. Okay, so that's an example and the definition, but some of you are probably thinking, why would I want to calculate a vector that is perpendicular to two given vectors? That's a really good question. So let me, and it has to do with torque, okay, torque in physics and engineering. So let me share my screen with you again. And here I am on Wikipedia, and let me just just narrate this. Loosely speaking, torque is a measure of the turning force on an object, such as a bolt or a flywheel. Okay, and if I open up this animated GIF, okay, let me just make that a bit bigger. Okay, think of the dark blue and the red vectors here as representing forces. Okay, you might have a spanner or a wrench that's working on a nut, and your hands on that big ball. So you've got two vectors, a position vector associated with the end of the spanner, and you're applying some sort of force with your hand, this green vector. Now torque acts sort of perpendicular to both of those two forces. It sort of acts along the bolt or something that the nut is attached to. Okay, so this is a case where you've got two vectors in a plane, the red vector and the blue vector, and you're interested in the force or the vector that is normal to both of those two vectors to measure the torque. Okay, all right, so that's a little bit on the motivation of where this cross product comes from and how it's motivated. Okay, now in forthcoming videos, I'll talk more about the dot product, and I'll introduce the scalar triple product, and I promise I'll do a derivation of this nasty form for the cross product and show you where it comes from. So I hope you can join me for those presentations. Thanks again for watching. If you have any feedback, put it in the comment section. Thanks again.